Thanks, Vijay, for the lovely introduction. I'm happy to be in Bangalore. And this is my first time in ICTS. And today I'm going to talk about electrohydrodynamics of epithelial tissues. So as you can see, as the name suggests, so it will deal with hydrodynamics of epithelial tissues, taking into account also the effect of electric fields. Now, what are epithelial tissues? So epithelial tissues are tissues which are made up of a large number of cells. They're tightly packed, and they can have polarity, and they come in all forms and sizes, as you can see in this picture. So, and all of them they perform different kinds of functions, like secretion, absorption of fluid and other materials in the different organs like heart, kidneys, you name it. So basically, you can see that they're found in the sacs of lungs, in the heart, in blood vessels, in kidney tubules, in uterus, digestive tract, etc. So most of the organs that are found in the human body, they have epithelial tissues. Now to give some examples, so this is an image of a corneal epithelium. And as you can see, there are lots of cells present in this epithelium. And this is the image of a Drosophila wing. You can also appreciate that there are plenty of cells making up this tissue. This is the image of a zebrafish neuroepithelia. So it also contains pseudostratified epithelial cells. And this is a human intestine organoid with a fluid-filled cavity inside. Now, today, I'll mainly focus on two kinds of tissues. That is, one of a thick tissue that is surrounded by fluid on both sides, and another will be to kind of modeling this kind of spherical tissues with a lumen inside. Now, what are the characteristics which define epithelial tissues? So some of the generic characteristics is that the epithelial tissues have cells which are tightly packed. So they have integrins and adherins proteins which are present in the junction of the cells, and they tightly bind the cells together. And there is also an apico-basal polarity. So there is an apical surface which faces the lumen, and the basal surface which faces away from the lumen. And there are also signaling pathways in the apical and basal side which are different. And this makes distinguish the apical from the basal side, and the tissue is considered to be polar. So there are also cells can transport ions and fluid in and out of the cells. They have ion channels in the membranes, which works to do this kind of functions. And this is very generic function for all kinds of cells in tissues. And also there are dynamics which takes place in the epithelial tissues, like cell division, cell apoptosis, cell rearrangements, cell shape changes. All these kinds of dynamics takes place in a typical epithelial tissue. Now, what is the tissue properties depend on? So one of the external factors that the tissue property depends on is external stress. So if you apply some stress, how does the tissue volume change? So there's an experiment which was done, so using mouse carcinoma cells, tumor spheroid. So they put these carcinoma cells in a cultured medium, and they formed a spheroid. What they found is that if you apply some external stress from outside using dextran, which is a neutral polymer, which is not metabolized with the cells, so it can apply some kind of osmotic pressure. So what happens if you apply osmotic pressure, you see that the tissue volume is reduced as expected. And then if you take away the pressure, it goes back to its original volume after a few days. So this is kind of expected behavior. And they show that also if you increase the pressure, the tissue volume reduces more and more. So all this is very expected. And what they find very interesting is that the cells divide mostly at the periphery and not at the bulk. So these blue cells that you see, they are basically the dividing cells. And as you can see, they are mostly at the interface. And at the bulk, there are very few cells which are dividing. And this is at zero pressure. But if you increase the pressure, the external pressure, what happens is the cells which are dividing the bulk, the number reduces more and more. So this is a plot which shows the division rate versus the distance from the surface. So you see that near the periphery, most of the cells are dividing. Now, with the increase in pressure, so with the increase in distance, this falls off drastically. And then with increase in pressure, it falls off with a more steeper slope. And then basically there is no division here. But here, if you have no pressure, very less pressure, then there is some division even inside the bulk. But that's very less.
Hydrostatic pressure, this is what is another question.
I mean, it can be a hydrostatic pressure. pressure from outside, basically. So you can have osmotic pressure, you can have any fluid pressure from outside, hydrostatic pressure, so this is, as this explains that pressure has an important role in tissue morphogenesis. Also, the tissue properties also depend on electric field. So there is an experiment which shows that these melanoma cells from humans, they treated it using a tumor treating field, electric field, as an AC current, and they show that the cell division gets arrested. So the mitosis of these melanoma cells get arrested at this position after 2 hours, and after 3 hours, they still find it in the same position. So basically, it cannot divide anymore. And there are also studies which showed that if you apply an electric field, the cell division axis gets reoriented in the direction of the field. So if you have this electric field, you can see that this cell is trying to divide, and then the cleavage becomes perpendicular to the electric field. The same is true for this cell also, like it's dividing here. And it's along the plane of the electric field with the cleavage perpendicular to it. So electric field plays also vital roles in cell division, and hence also affects tissue properties in certain ways. So what are the relevant questions one can ask for epithelial tissues? So one of the questions is how to describe the fluid transport phenomena using a theoretical framework for tissues. And another question is how does the tissue growth depend on the ambient surroundings? Like if you have fluid or any kind of other materials outside, how does it affect the tissue growth? And also how does external fields like electric field or magnetic field regulate the tissue growth properties? So these are the questions we'll try to answer in our model. And there are various models which have tried to explain this kind of answers for tissues. And one of them, they go on from discrete to continuum descriptions. So for discrete models, the most popular model is the vertex model, which takes into account the position of the vertex and how it evolves with time. And also, they take into account a target shape, a target perimeter, a target volume, and this minimize the energy to get an optimal shape and size for the tissue. Now, you also have continuum descriptions, where if you have a large number of cells, and if you want to take into account a multi-layered tissue. So here, for example, you have a layer of tissue with large number of cells. You can approximate it as a viscoelastic interface. And viscoelastic interface will have elastic response at short time scales, and will have a viscous response at very long time scales. So if you shear, stretch, or bend the tissue, basically, you will have elastic relaxation at short times. But then there will be also T1 transition, cell division, cell apoptosis, which takes place over longer times, and you will have some viscous response. And generally, this kind of viscous long time behavior is very well modeled using hydrodynamics. So we will use hydrodynamics in the model, as I'll show in the future slides. So this is the outline of my talk. So I'll talk about hydrodynamics of tissues, and I will touch upon force balance and how active pumping is done by the cells in the tissues. And then I'll talk about two of the models. So one is thick epithelial tissue surrounded by fluid on both sides, and there'll be a spherical tissue with a lumen inside. And both these works have been published the previous year. So the hydrodynamics of tissues, so how to take into account how to construct a hydrodynamics theoretically for tissues. So what we need is a coarse-grained description of the tissue. So you take a patch of cells and you take the average velocity, average orientation of the cells, and denote it to a small a particle inside. So basically you can say that one of the particles have the velocity and the orientation, which is the average of the velocity of all this of the cells on the orientation. And you take, similarly, you take patches throughout the tissue, and this is kind of how you coarse grain the tissue. And we take into account a two-fluid model, that is, we have cells, and also you take into account interstitial fluid, which flows in between the cells. Now, we can write down a cell balance equation, so that is, if the number density of the cells is denoted by NC, then the rate of change of the number density of cells has terms which comes from convective derivative, and also a source term which comes because of the cell division rate and the cell apoptosis rate. So this is a net cell division rate which can contribute to the cell number density. So in this paper, they also take into account mass conservation of the tissue, the constant cell and fluid density of the tissue, and also tissue incompressibility. So if you apply too much pressure, of course the tissue will break, but the pressure we are talking about is quite small in this regard. So tissue incompressibility can be a good approximation. And now we go to force balance. So to study force balance, we require to denote cell stress by sigma C alpha beta and fluid stress sigma F alpha beta, where the superscript C and F refers to cell and fluid respectively. And the cell stress consists of two parts, the isotropic part and the anisotropic part. So the anisotropic cell stress comes because the cells can divide and die, and all these are anisotropic, contribute to anisotropic stress inside the cell. And also the fluid pressure consists of an isotropic part. So there is no anisotropic fluid stress we have taken into account because the fluid particles are quite small compared to the cells. And so the anisotropic fluid stress is considered to be negligible compared to the isotropic fluid pressure. Now the total force balance in the Stokes limit can be written like the divergence of the total stress is equal to 0. And this can be divided into two parts. So one is the force balance for the cells and the other for the fluid. And here F alpha denotes the momentum exchange between the cells and the fluid. So the F alpha is given by this kind of expression where this is the proportional to the relative velocity difference between the cells and the fluid, with kappa as the permeability. Now, moving on, so cell division and death, these are the phenomena which can fluidize the tissue at long times. And at long times, and the viscous limit, you can write down the stress, the isotropic cell stress as consisting of homeostatic pressure and the viscous term. So this homeostatic pressure is the pressure at which the cell division and apoptosis, they balance each other, and and any deviation will create a cell stress, right? And this is the viscous stress with Vc alpha beta is a strain rate tensor. Now you also have cell division, cell death, which gives rise to anisotropic cell stress. So the anisotropic cell stress consists of also contribution from the viscous stress. And since the cells are polar here, we also have an oriented cell growth kind of active pressure, which comes due to oriented cell growth. And
the viscous term comes like for the anisotropic case, cell division or whatever, 2 eta something.
Yeah, so this is the shear viscosity, and you have if you have a shear, if you apply.
Understand the physics, like basically you have a cell division taking place.
Yeah, so that's given by basically this term we are talking about.
The orientation.
Yeah, that's the orientation thing. So if you have cell division death, these are quite anisotropic in general, because the nucleus comes down to one of the sides and then it divides into two cells. So what happens is that because of that, like you have some anisotropic stress growing inside the cell, and that's one of the contributing factors to this anisotropic cell stress. Also, there is also, you can say that this term also has contribution from actin, cytoskeletal dynamics, all these things.
And why does the first term appear?
The first term is a shear term. So if you have a shear, because
cancelled out, like it's when alpha is not equal to beta, right?
This one, yeah. Alpha is not equal to. If alpha is equal to beta, you have the term in the isotropic cell stress. Yes. Okay. Can I move? Yeah. Okay, so now moving on to the pumping phenomena in the tissues. So how to incorporate active pumping, the fluid pumping and the ion pumping in a theoretical model. So basically you have the tissues, the cells have ion pumps, which basically take into account the fluid flow and the ion flow throughout the cells and inside the tissue. So we need to consider electric fields and electric currents also. And to do that, we need to take into account the charge conservation equation, where rho is the charge density, J alpha is basically the current density in the tissue. Now, the cell number density is basically a function of isotropic cell stress, the anisotropic cell stress, and the electric field. Now, what you can write down is that since it's a function of all these dynamical quantities, you can write down an equation which, where the rate of change of the cell number density consists of all these three terms. Now, this first term basically denotes the rate of change of cell number density with the isotropic cell stress. The second term, the rate of change of cell number density with an isotropic cell stress. And the third term is the rate of change of cell number density with the electric field. And the second equation, there's a polarity.
It's a directional thing, or is it some electric polarization?
No, it's directional. It's directional polarity.
Why is the P dot E there?
Yeah, so the thing that we considered here is that the electric field is also in the z-axis. So the electric field basically orients the polarity also, kind of. So that's why you have P dot E in the. That's the lowest order term you can have.
Sure. Why does it orient? What's the physics?
I mean, as you have seen, that electric field, as I've shown in one of the previous slides, that electric field can orient. Yeah.
You're saying if they both are oriented together, then if they have a rate of change of that,
yeah,
it will decide the number. Why is that?
I mean that the cells can divide or die with the electric field can basically provide a force for the cells to divide or die.
Why is it the time rate of?
Yeah, why is it d by dt? Like just P dot E, they're not aligned, then maybe it will stretch or pull.
I mean, that's why it will try to align, and I mean, yeah. I mean, it will try to align, and then I mean the cells basically. That's why if it aligns, and then the cell division or this apoptosis they take place, right?
So do you have a separate equation for P as a function of E?
No, here we have considered basically the P to be uniform, the polarity to be uniform. We haven't considered so that of course you can write down an equation for constitutive equation for the polarity. But for simplicity, we haven't considered the fluctuations of the polarity in this model.
E is also some fixed given.
E can be fixed. No, E is not. Sorry, E is not fixed. The current is fixed. The electric field can vary. Yeah. Yeah.
I'm still confused with the first equation. Can't you just eliminate a total derivative there? And just write log NC as equal to.
I mean, probably, but yeah, you can also. I mean, basically, since it depends on all these quantities, so it kind of makes sense to write it different terms for that. I mean, what happens is that I'll show that that if you take these two equations, these two are kind of same equations. So if you equate them, what you will get is a constitutive equation for the isotropic cell stress, and that will be a Maxwell constitutive equation for isotropic cell stress. And if you take basically the viscous part, so then it boils down to the constitutive equation for isotropic cell stress, which we use in our model. And that contains contribution from the homeostatic pressure, the viscous term, the anisotropy part of the cell stress, the electric field, and also the change in the velocity, the difference in velocity between cells and fluid. So I mean, this is a phenomenological equation, and it can be like, you can take into account all the terms that can give rise to it. And similarly, we can also write down a phenomenological equation for the anisotropic part of the cell stress, and it also contains the viscous part, the part which comes from the nematic part of the tensor, the part which comes from the symmetry traceless part of P alpha E beta tensor, and also the symmetry traceless part of this difference in velocity contribution. And the local net cell division rate, that is Kd minus Ka, is proportional to, also depends on all these dynamical quantities. But you see that there's a PCH, the homeostatic pressure. So if homeostatic pressure is, at homeostatic pressure, the division rate and the apoptosis rate exactly are equal. So Kd minus Ka will be 0, but if you deviate from the homeostatic pressure, then Kd minus Ka will be finite. And it will depend on all this, the isotropic stress, the anisotropic stress, and the electric field. Now, the momentum exchange force that I talked about, so it depended on only the difference in velocity between the cells and the fluid. But now, since we also want to incorporate the fluid pumping effects and the electric field effects, there will be other terms which needs to be added. So this is the friction term. This is the term which comes from the active pumping term, so it's proportional to the polarity we have taken. And there will be some electroosmotic effects due to the electric field. So if there is an electric field, there will be a velocity of the tissue components. And there will also be a contribution from the distortion of the nematic tensor. So basically, if the polarity is the spatial distortion in Q alpha beta tensor will also create a force. Now, similarly, using the same arguments, you can write down an equation for the current density of the tissue. So this is the ion flow, the first term. The second term is the ion pumping, which is also proportional to the polarity. The third term is electric effects, which is the electric conductivity terms. And the last term is basically comes from the distortion of the Q alpha beta tensor, but it has a name which is called the flexoelectric effect. So flexoelectric effect is the effect which comes because if you kind of bend the tissue, then what happens, the charges they redistribute and the polarities also gets distorted, and this gives rise to an electric field. So this is a flexibility. And you'll see that this effect is not important in any planar tissues, but if you have a curved surface like a spherical tissue, then it will have some dire consequences.
Can you explain what is del by del beta, like what is beta and
Beta and
the last term, flexoelectric.
Flexoelectric effect, yeah. So Q alpha beta is the nematic tensor.
How do you get that del by beta? How do you derive that term?
This term? Oh, this is written from purely symmetry argument, but it's just the distortion of the tissue. Like if you bend the tissue, like what happens, these charges they distribute and the polarity direction also, they get bent, right? So this will give rise to an electric field. So that's a flexoelectric effect. Yeah. And so now I start with the first model, that is a thick epithelial tissue with fluid surrounded by both sides. So this is the tissue and the blue region is the fluid. And I placed a permeable grid at the bottom. So the permeable grid allows the fluid to pass through, but doesn't allow the cells to pass through. So it acts as a filter for the cells. And since the grid is fixed in this position, the tissue can grow only in the upward direction, but is not allowed to grow across the permeable grid. So now the external pressures due to the fluid are P1 external and P2 external on both sides. The osmotic pressures are Pi1 external, Pi2 external. And the velocity of the external fluid is represented by Vf external, and the polarity of the tissue is in the z direction. Now, as you might have realized that I have taken basically everything in the z direction. So this is basically effectively a one-dimensional model. So I am not considering any variations along the xy direction. So all the variations along the z direction. Now for boundary conditions, you need to apply stress continuity. So the stress needs to be continuous at both the interfaces. Then we need to take into account fluid permeation at both the interfaces. And also we need to take into account different growth rates at both the boundaries. Now this comes from the fact that, as I have shown in my previous slide, that there is a cell division rate which is very different at the interface, and not at the bulk, it doesn't divide so much. So that's why we took into account that by using different growth rate. And that will translate to different surface growth velocities at the interfaces. So at z equal to 0, there will be a V2, a velocity, and at z equals h, we have V1. Now if V2 is 0, then it will translate to the classic no-slip boundary condition here for the cells. And if V1 is 0, then basically the dynamics of the interface is represented by the velocity of the cells at the interface. And we also impose incompressibility and charge neutrality of the tissue. So charge neutrality means the tissue is considered to be electrically neutral. Now, taking all these boundary conditions, we'll solve for this model, and we'll find out the thickness dynamics and the state diagram. So the thickness dynamics comes from, if you write down the force balance equation, you will find that it boils down to this hydrodynamic equation for the cell velocity. And here lambda naught is a time scale, A is a, the lambda naught and A, these both are length scales, and V lambda comes out to be a characteristic velocity. So lambda naught is basically the permeation length scale. So the length that how much the fluid can permeate per unit time. And A is the length scale which comes because of the electric effects. And V lambda is basically the velocity which comes because of the renormalization of the electric field of the external velocity where the electric field affects. And now if you use the boundary conditions to solve this equation, you boil down to a dynamical equation for the tissue thickness. So dH dt is a function of h. H is the velocity. So the
tissue is incompressible.
Yes.
The velocity has no dependence in the x and y direction.
Right.
You still have derivatives in the y z direction.
In the z you can vary. Yeah. So everything varies in z. Nothing varies in x and y. Otherwise, you would have a three-dimensional kind of equation, right? So, yeah. So,
in a sense, the tissue is actually contracting in the xy direction.
No, tissue, we don't consider at all anything in the xy direction. It's just that it's either growing in the z direction or it's shrinking in the z direction.
Yeah, but then if you want incompressible, should you contract or extend in the xy direction?
So incompressible means, yeah, you can say that, but yeah, you can say that. But it's kind of taking into account volume conservation, right? Yeah. Yeah.
It's incompressible, but the volume occupied by the tissue is changing.
Yeah. And the volume is like, the tissue is just made up of cells and fluid. So if the cells kind of die, they convert into fluid, or the fluid, if they divide.
Incompressibility is statement the density of the tissue doesn't change.
Yeah, the density, the cell density, the fluid density, they remain constant. Yeah. So if you use the boundary conditions, you obtain the velocity, the thickness dynamic equation. So this is the equation. And even if I don't write down the explicit form of function of h, you can appreciate that if fh is less than 0, then dH dt is negative, then the tissue shrinks. If fh is equal to 0, then you get a finite steady state tissue thickness. And if fh is greater than 0, then dH dt is positive and the tissue grows. So taking this into account, now if we plot the dH dt versus h, so if you find out the dynamics at positive surface growth velocity, we get this kind of behavior. So V2 greater than 0 means the surface growth velocity is positive. The cells are dividing at the grid. And the cells are dividing and they're moving upwards from the grid. So what happens is that if they're dividing, if you have a small current, it can give rise to a steady state here. Now, if you increase the current, what happens that it can give rise to two fixed points. So one is the stable fixed point, the other one is the unstable. So if your initial thickness is somewhere here, so you'll converge to this steady state fixed point, but if your initial thickness is above this cutoff, then the tissue will proliferate. Now, if you increase the current even more, what happens? The tissue just proliferates. You don't have the steady states anymore. So this is the behavior at positive surface growth velocity. And if you plot the steady state profiles, you have the steady state profile for the cell velocity. So you see that the cell velocity, basically the cells are dividing at the grid, and then they move towards the interface, slowing down, and the velocity becomes 0 here. So, and the cell Kd minus Ka, the net cell division rate, is basically here the cells are dividing at the grid, and then it's basically dying throughout the bulk of the tissue. And the apoptosis rate is more near the grid, and as you grow towards the interface, the apoptosis rate slows down. And similarly, if you plot the stress for the cell stress profile, you see that the cell pressure is very high at the bottom, and as you grow towards the interface, the cell pressure also reduces. And the fluid pressure is the opposite, that the fluid pressure is very low here, and it increases as you go towards the interface. So all these are kind of expected behavior. And if you now plot the dynamics for the negative surface growth velocity, that is V2 less than 0. So V2 less than 0 means the cells are basically dying at the grid, and it can only divide at the top. So if you have a current, small current, nothing happens, the tissue just shrinks. Basically, it collapses. And if you increase the current a little bit more, so there's an electric field. So if the current in the positive Z direction means it's from the bottom to the top. And it gives an electric field which allows the tissue to grow. So basically, you can have two steady states again. So one is unstable, the other is stable. So if you have very small tissue thickness, the tissue will shrink. But if you have the tissue thickness is somewhere here, so it converges to the steady state thickness. Now, if you increase the current even more, you just get this unstable fixed point. So if you are above this thickness, the tissue proliferates. If you're below this, the tissue shrinks. So taking all of these things into account, you can plot a state diagram for this model. So this state diagram is current versus velocity. So the external current versus external velocity for positive surface growth velocity and negative surface growth velocity. So positive surface growth velocity, you have either, depending on which region of phase space you are in, so you are either in the proliferating state, or you are in the finite tissue thickness state, or you are in the coexistence phase where you have both the fixed points. And here also, like for negative surface growth velocity, either the tissue collapses, or either there's unstable fixed point, or you have the coexisting phase in between. So that's the state diagram you obtain from that. Yeah. So to conclude the first part of my talk, so the cells, basically we have developed a model which takes into account the pumping of the fluid and ions by the cells throughout the tissue. And the dynamics of the tissue depends very much on the growth velocities at the boundaries, that is V1 and V2. And also depending on the external current and external fluid velocity, we can obtain tissue collapse or tissue growth or steady state tissue thickness. Yeah. So if you have any questions regarding the first part, you can, okay. So now I go to the last part of my talk. So it's a spherical tissue with a lumen inside. So this basically is trying to model like this kind of spheroids from carcinoma cells, or this kind of spherical organoid with a lumen inside. And basically you can approximate it by this kind of tissue structures, spherical tissue with a fluid filled cavity. Now, one of the important questions we ask here is what factors are responsible for lumen nucleation? So how does the lumen nucleate? Or more explicitly, is if you start from a very small lumen, like how does the lumen grow or it shrink? So what are the dynamics of the lumen, basically? So the boundary conditions are basically the same as in the previous case. So we consider stress continuity, we consider fluid permeation of the boundaries, and different growth rate at the boundaries. Since the tissue is curved, we have surface tension, gamma 2 and gamma 1 at both the interfaces, because it can have Laplace pressure because of the spherical shape. You also have the external pressures, P1 and P2, and Pi1 and Pi2 are the osmotic pressures inside and outside. And this is also we consider it spherically symmetric, so it's basically only one dimensional, so every variation is along the radial direction. And the polarities along the radial direction also. Now, so if you write down the dynamics of the spheroid, and what you do is you write down the bulk equations, and using the boundary conditions, you get a differential equation for both the interfaces, R1 and R2. And these are the equations. Now, you cannot solve this analytically, so we have solved them numerically. And what we find is that there are a bunch of possibilities. So you have lumen nucleation, so basically starting from a spheroid, the lumen can nucleate. Starting from, so you also have growing spheroids. So the spheroid can grow without any lumen. The spheroid can grow with a fixed lumen. The spheroid can grow, and the lumen can also grow. And the spheroid and lumen can grow together as a monolayer.
So when the lumen thing starts, is it like a new interface is generated there?
So that should be, but yeah, in our model, because it's very difficult to start from nothing to, like how to theoretically describe, I mean, to do that. We don't know how to do that. But what we did is starting from a very small lumen, which is like very, very small, how do you, whether the lumen disappears or the lumen grows.
You don't have a cost to that interface, that's what you're saying.
Yeah. I mean, the cost comes from surface tension, but you have to consider a lumen, small lumen at least for that. Yeah. So you can also have steady state spheroids. So the lumen and the spheroid are at steady state. The spheroid is at a steady state with no lumen, and the spheroid and the lumen together as a monolayer is at steady state. And you can also have oscillating spheroids. So the lumen and spheroid both can oscillate. So we'll mainly concentrate on the lumen nucleation part here. So basically, we try to concentrate on the early stages of lumen formation. So what happens if R1 is very, very smaller than R2? So what happens is that the dynamics of R1 and R2 in that limit partially decouples. So R2 is then independent of R1, but R1 still has dependence of R2. So you have this equation for the volume of the lumen, which is a function of psi, which is a function of R1, R2 basically. So psi contains this surface term and the volume term. And this is the volume of the lumen. And this is the effective surface tension. So you see the effective surface tension consists of the surface tension of the lumen and also the term which comes from flexoelectricity. So this is a very important contributor to the surface tension. So it can either make the effective surface tension negative or positive because of that. And also this function of R2 consists of an effective pumping term and the pressure term and effective pressure and all these other terms. Yes.
And you have a radial electric field here?
Radial.
How do you radial electric field? You have to have some charge somewhere.
No, yeah, so you can have, so you saw the constitutive equation for the current I showed you. So that's how you get the electric field from there. So if you impose a current, you can get an electric field from there.
So how can you get a radial electric field?
So radial electric field is like you apply the electric current radially. Yeah. I mean it's theoretically we try to simplify it, saying that okay, the electric field is also radial. Yeah, I know, like it should be like in one direction or something like that, right? But let's say we have like the ions are, let's say they are kind of radially distributed or something, but then the tissue is also neutral, so the charge is neutral, and but you have an electric field. So yeah, so there's also an effective pumping, which is lambda effective, which comes from the pumping parameters I showed, and this can also be positive or negative. So this is a flexoelectric coefficient, lambda 4, and as you will see that this can make it this positive or negative. So depending on like whether this term dominates or this term dominates, you can have psi positive or negative. And if psi is negative, then the lumen will grow, and if psi is positive, then the lumen will shrink. And if it's 0, then the lumen will go to a steady state thickness. So for function of R2 greater than 0, you get this kind of behavior. So basically for psi, that is this term dominates at small r1 and this term dominates at large r1. and there's a critical radius in between, which is the maxima. Now, if you decrease the surface tension, effective surface tension, what happens? This minima reduces and ultimately disappears. So the lumen basically can grow, can shrink. The lumen shrinks if you are in this part, if you start from here. But if you are in this part, the lumen can grow beyond this critical radius. But if you decrease the surface tension, look at these two clubs. So here there is no barrier. So the lumen can grow spontaneously. Now, what happens if f of R2 is negative? So you get this kind of profiles. So basically the lumen always shrinks. Now, if you decrease the surface tension again, what happens? That you come across minima like this. And so the lumen comes to a steady state finite thickness. So basically, whenever you reduce the surface tension, there is a possibility for lumen formation. So the lumen forms whenever this is negative, this effective surface tension is negative. That is the flexoelectric coefficient, this term from flexoelectricity overcomes the surface tension of the lumen. Also, the pumping effect is also very important. That is, the lumen grows for large spheroid. And yeah, the pumping can also make if this function positive or negative, basically. So now I go to the state diagram and I will talk about the oscillations. So the state diagram we have plotted in effective pumping versus effective surface tension phase space. So you see that if effective surface tension is negative, as you have seen before, the lumen will always be there. So in this part of the phase diagram, so when lambda effective is also positive, then both the lumen and the spheroid can grow, or the lumen and the spheroid can grow as a monolayer. And here you have steady state of the lumen and the spheroid. And here in this red region, you can have oscillations of the spheroid and the lumen. And when both of them are positive, the lumen can either, like the spheroid can grow or it can shrink. Yeah. And when this effective pumping is negative, the lumen, there is no lumen, the lumen closes. Now, to come to this oscillation, so I'll talk about this broken line here. So how does the oscillation change when you go from this part to that part? Like when you increase the surface tension, basically. So what happens when you are just entering the red region, when the surface tension is low, the oscillations are very small. They are quite small oscillations of the lumen and the spheroid. When you go to a bulk of the red region, with the increase the surface tension, what happens? It starts to have rapid oscillations. So the lumen grows to a very small size, and then it oscillates back to the size of the lumen, and then it follows periodically. So, and if you go towards very high surface tension, then this lumen and the spheroid, they oscillate in a sinusoidal manner almost. So this is so the oscillations come out naturally from a model here. So to conclude, we have developed a coarse-grained hydrodynamic description of a spherical tissue with a lumen inside, and taking into account electric field effects and pumping effects. And as you have seen that flexoelectricity and pumping, these are very important effects in this kind of tissues, in lumen nucleation effects. And also there's a large variety of behaviors we get at long times. So you either get steady states, lumen shrinkage or lumen growth, or all these kind of possible behaviors, and also oscillations. So this is the conclusion. Now, what you can, in the future direction, where you can go is that, so since the tissue, we have considered the interface to be uniform, but you can consider the the interface to be fluctuating also. And you can also consider the polarity to fluctuate. And then you will be able to study thickness instabilities and correlations in this kind of structures. And also, we have only considered planar geometry and a spherical geometry. You can consider in principle, you can any arbitrary shape. Also, we have only considered electric effects in this system. So studies have shown that if you give electromagnetic fields in the tissue, then the cells can orient in a vortex kind of fashion. So this is another interesting way to study topological defects. And also, like we don't know yet like whether this hydrodynamic formalism can be extended to study epithelial to mesenchymal transition. So epithelial cells are cells which have showed that they are tightly packed and they're like, they're tightly packed, they have polarity. And mesenchymal cells are basically, they're floating around, they're motile, and they don't have any polarity. So what happens during this epithelial to mesenchymal transition is that the cells lose the epithelial markers and they gain the mesenchymal markers. And this is found in many different tissues, especially in cancer cells. So cancers, when they metastasize, they go from epithelial kind of features, they lose the epithelial features and gain the mesenchymal features. So we were like speculating if this hydrodynamic formalism can be extended. So one important thing we need to take into account is the cell volume fraction to not be fixed, so that it can also has a dynamics. So we need to take into account the dynamics of the cell volume fraction, the cell polarity, and the tissue thickness, and the interplay between them, so as to maybe study this kind of epithelial to mesenchymal transitions. And another interesting thing is that in the last 2 years, people have found that using numerical analysis, that tissues, while going from jammed solid state to a fluid state, they pass through a hexatic phase in between. And this hexatic phase is basically, they're characterized by no translational order, but quasi-long range orientational order. So we are also thinking of like studying the hexatic behavior in tissues. So we are trying to at first develop the hydrodynamics for the hexatic phase, and then we'll go to that. So so can this model be also extended to understand cancer metastasis? And we don't know, but it's worth a try. So to acknowledge, I'd like to thank Frank and Jacques Prost for suggesting me this problem and helping me out with various things, and Charlie for doing the simulations in case of spherical epithelium. Also Keisuke, Orgodip, and Marco for enlightening discussions, and the whole biophysics group for the encouragement and support. And thanks for your attention.